Hello and welcome back. Lecture number 2. We continue with complex variables. Today we're going to be looking a little bit at Laurent series and probably define properly what is a residue. Not properly because I'm not a purist, I have to correct myself there. In an applied sense again and a little bit on an intuitive kind of manner. Okay, what have I got? Where's my worker? Oh, I put it up here. I've got 4 functions to do some Laurent expansion, so that should be enough because really we don't need more than that. Next lecture I'll be doing some residues, some computational residues. So let's start with the first function that we got up there. Let's see, we briefly mentioned Laurent obviously on the first lecture when we did look at poles and singularities and also that sort of stuff. So the first function is a very simple function. It's f of z is equal to 1 over z. What does the question say? It says determine a Laurent series for f of z is 1 over z, which is valid in the infinite annulus mod z minus 1 is bigger than 1. Okay, first of all, what does that mean? If we look at this particular, let's look at the picture, probably is better. We've got the complex plane here, and we've got the origin here. Quite clearly, this particular function has a singularity at the origin, and at the moment, we want to do an expansion centered, if you want, at positive 1, so at this point here. So there's 2 choices that we have in order to do this particular expansion. We can either expand center at the origin, and we can do, of course, any radius if you want, so long as we include the origin, so it's centered at the origin. It's all good, okay? So a circle like this, but of course this Laurent expansion is quite stupid really. It's already expanded, it's 1 over z, but we can center it anywhere else we want. So at the moment it's choosing to put the center at 1, and then we have 2 choices, okay? We can actually expand around a circle, let's say a small circle which does not go through that singularity. As long as it doesn't go through it, is fine. So this is actually the circle mod z minus 1 is less than 1. They don't want this particular one. They want us to go on, draw a circle which actually is of radius 1, so it will be going through the origin, but they want us to have the expansion to be valid on the outside of this circle. Okay, so that's called an infinite annulus. Okay, going on forever. Okay, so the expansion will be valid in there, and it will be, of course, in powers of z minus 1. So how do we do something like this? It needs a little bit of manipulation. A lot of this Laurent will probably require mostly binomial expansions. The standard expansions of 1 plus x to the power of minus 1, should really be writing z there, or 1 minus x to the power of minus 1, and a few other standard expansions. So for this one, I'm going to create my z minus 1 to be bigger than 1. So first of all, I'm looking at this line here, and I probably want to, because it's 1 over z, I want to use one of these 2 things here. But of course, let's write it in z, or actually in w probably be better. Okay, so if I have something like this, the modulus of w must be less than 1, whatever my w is, for this expansion to be valid. So at the moment, they're saying to me the modulus of z minus 1 must be bigger than 1. So quite clearly, if I flip it, so I go for this version, that will be less than 1. So I need somehow to create things which look like that. The way I will do it, of course, is I'm going to say, well, z minus 1 in a bracket. Of course, I need to balance it, plus 1. Probably rewrite it for simplicity as 1 plus bracket z minus 1. And then what can I do after that? I'm going to factorize out of this denominator. I'm going to factorize a z minus 1 in a bracket like this. And inside the square bracket, I'm going to have a 1 over z minus 1, that of course is my 1 when I multiply it out, plus 1. Okay, 1 on the top. Well, how does that help me? Well, first of all, this is going to be 1 over z minus 1. This is this bit here, and I'm going to write this expression on the top as 1 plus 1 over z minus 1 to the power of minus 1. So what I have done in there, I have achieved the expansion of 1 plus w to the minus 1, which is a standard expansion. I'm going to write on the side here. And of course, keep in mind, this expansion mod w is valid for the modulus of that being less than 1 now, which is equivalent to the modulus of z minus 1 being bigger than 1, which means I'm outside there. So let me just write the expansion of 1 plus w. I'll actually write it on the bottom here, probably better. So 1 plus w to the power of minus 1. It's a standard binomial. It alternates this one. So it's 1 minus w plus w squared minus w cubed plus higher order terms. Okay, so using this particular expansion, what will happen here is I'm going to have 1 over z minus 1. That's the item which is pulled outside, bracket, and I have 1 minus 1 over z minus 1, that's my w essentially, plus squaring it now, alternate the sign, 1 over z minus 1 all cubed plus higher order terms, plus hot. Okay, so all I need to do is to just multiply it out. Shall I multiply it out? Shall I just write in sigma notation? Probably better to maybe write in sigma notation. So what I'm going to do, I'm going to leave that on the outside for the time being and multiply it afterwards. So this is sigma. And what do I have on the sigma? I'm going to have powers of z minus 1 at the bottom. So I'm going to, let's say we run it from 0 to infinity, and I'm going to need to alternate on the top, so I need the minus 1. So for that to work, the first thing has to give me a 1, so it needs to go to the r is equal to 0, r is equal to 1, r is equal to 2. And I think if I put r, it also works with a plus and minus, because of course to the 0 will give me positive, so that's all good. And of course, I'm just going to save myself a line, I'm not copying that again. I have this extra item on the outside. I'm going to put it inside now. Okay, and this will increase this to the r plus 1. Okay, and this is the Laurent expansion of f of z, which is valid outside this particular circle. It's a little bit messy now to see. The circle is basically centered at the, not circle, I beg your pardon, on the outside of the circle if you want. So that's 1, and the circle has radius 1. Okay, so this particular Laurent works outside this circle. Okay, so that is question number 1 done. Okay, what is question number 2? Question number 2, it's kind of similar. There's a different function. We've got 1 over z squared minus 1. So the first thing when I look at this, I'm probably thinking partial fractions, but I need to look at it in a little bit more detail before I attempt partial fractions. I want to see what kind of expansion they're after. Z squared minus 1. Let's put this one in the middle, otherwise it might fall off. Okay. Determine the Laurent series for f of z is 1 over z squared minus 1, which is valid in the punctured disk. I don't want to talk about punctured disks. It's just a little technical thing I'll explain. Mod z minus 1 lies between 0 and 2. So let me just, I'll explain a little bit about this particular function before I do anything. The choices that we have. And then I'll explain what the question is actually asking. Let me just break it into partial fractions, factorize it rather. Z plus 1 and z minus 1. So this particular function has singularities at plus and minus 1 on the real axis. So let's have a look what we can do. What choices do we have? So this is the 1. And this is the negative 1 on the other side. Okay, we can do expansions. We can expand in a circle. Let's say my choice, which is centered at the origin. Okay, mod z, and it does contain, let's say, is less than 1. So something like this. Okay. I can expand and find a Laurent, that means in powers of z basically, on a circle or actually it's not a circle, it's the outside of the circle, which is outside the circle, again, centered at the origin, but is outside both of those singularities. For example, okay, so the outside, like we had on the previous example. What other expansions can I do? I can actually center at positive 1, so z minus 1. So I can have a circle which it has a radius which can be, let's say, up to 2. So it's something like that. So it only contains the z minus 1. So mod of z minus 1 is less than 2. Some circle like this. It just contains the at the center, the 1, and it can go as far as this particular singularity on the other end. What else can I do? I can do the exact opposite, or the complement if you want. Z minus 1 is bigger than 2. So the center is still here, but this time the radius is big enough to contain, of course, this singularity. That's at the center, and this singularity is also included inside my circle, if you want. Not inside my circle, I beg your pardon. I'm saying stupid things. So my circle is at 1 and is bigger than 2. So on the outside of this particular circle. I can do the same thing with the other one. So I can center it at negative 1. So z plus 1, and I can have, for example, these are just not the only choices, of course, yeah? Less than 2. So that's on the interior of a circle. Let's say something like this. Or z plus 1 mod z is bigger than 2. So this time I'm on the outside of a circle which is centered at minus 1 and it contains the other singularity. So these are just different choices. Okay, so what does the question says? It says to me I need to be valid in the disk which is, let's have a look which one of these they want, is less than 2. Z minus 1 is less than 2 and is bigger than 0. All that means basically is my center of the circle is at 1. Is where the center is, if there's a pole there on the Laurent, is kind of like a little technical point. I would ignore this particular one. Is as good. It's because it's probably an exam question and they want to be well defined. So that's all good there. So we want an expansion which satisfies that. So if I try to draw this, can I just draw that? Z minus 1 is less than 2 is, for example, some circle which looks something like this. Okay, as long as less than 2, it only contains this, this at the center and the other singularity on the outside. So how I'm going to do this one? Okay, do I go partial fractions for this one? I don't like the idea of that. It's actually quite stupid. I'm going to factorize, if you want, the 1 over z minus 1 in a multiplicative sense. So essentially I've just written that bracket, but the second one, this z plus 1, I'm going to write it. I want to create, if you look at this particular thing, again, I want the expansion. I'm going to rub it off afterwards, possibly of 1 plus or minus w to the minus 1. So the mod of w must be less than 1. And I'm looking at this line here, and I would like to make this particular thing less the modulus of z of minus 1, if I divide it by 2, to be less than 1. So I'm trying to create this thing here. So before I create that, with my z plus 1, I need to create the z minus 1. So I'm going to say z minus 1, and I have to balance it to be plus 1. So I need 2 there. So 2 plus z minus 1 is exactly the same as this. Now, and write it like that as well, so you can actually see what's about to happen. Okay, after that, this I'm going to leave, of course, as it is, 1 over z minus 1. And then I'm going to factorize out of this denominator just half, not half, actually 2, half out of the whole fraction. So this will look as 1, that's the 1 from there, 1 times 2, plus z minus 1 over 2. Okay, so what I've done now, I created the expansion of 1 plus w to the minus 1, this quantity here, where w is all of this, and of course this is valid for mod w is less than 1, which of course, this is my w, is of course that, which equivalently is what I was being asked to do. So this expansion, I wrote it on the previous one, is the one that alternates 1 minus w plus w squared minus w cubed plus dot 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 dot. So I'm going to do it as we're going along. First of all, write this on the top as I'm going to put the 2 at the front here, 1 over 2 z minus 1, so that's all good, okay, and write this bracket as 1 plus z minus 1 over 2 to the minus 1. Standard expansion now, merely substituting my values, square bracket 1 plus w z minus 1 over 2, no plus, sorry, minus, this is the one that alternates, minus, plus, squaring it now, w squared, so z minus 1 all squared over 4, minus plus minus, keep making mistakes, I've got a pounding headache today. I hope I'm not coming down with anything, or perhaps or even COVID or something, over 8 plus dot dot dot, and let's see what happens there. Do I write this as a sigma notation? Do I multiply it first? Probably I'll do it in sigma. Let me just rub this off. Hope I haven't made any silly errors there. I'm very error prone. Those who are using my work, my booklets and my exam papers and things, they know that I cannot even write straight from one line to the other. So let's hope I don't make mistakes here. If I do, please, yeah, well, you can laugh at me, I guess. It's no problem. So this is in sigma notation. So this is gonna be, let's run it from 0 again. To infinity. And what powers do we have? We have a z minus 1 on the top, and this will run to the r, so this will give me to a 1, and the 2's at the bottom, 2 to the 0, 2 to the 1, so it's going to be 2 to the r. Does that work? Okay, and I forgot the alternating factor, minus 1, and that again will be to the r. They're all r's, and nice and straightforward. When r is equal to 0, that is 1, that is 1, that is 1, positive, and of course after that it works. And all I need to do now is to multiply this inside, so it doesn't really matter how you write it. So this is going to be r is equal to 0. I'm not going to change dummy variables to 1 if it looks a little bit ugly. I will leave it as it is. So z minus 1, this will cancel me 1 from this bracket here, so it's going to go r to the minus 1. The minus 1 will stay as it is to the power of r, and we're going to multiply by another 2 on the denominator, so it's going to be 2 to the r plus 1 or something along those lines. It doesn't really matter. I'm just at the moment trying to get you to see different techniques of getting Laurent expansions in different regions, sort of like circles, exterior of circles, annuluses, and is it annuluses or is it annuli? I'm not quite sure. Sorry, my English is very bad as well. Okay. So this was question number 2, and now we're looking at question number 3. Different f of z. Different technique required for this particular Laurent. So f of z is z plus 2 sine of 1 over z minus 2. And the question says determine a Laurent series for this about, so it says about z is equal to 2. What does that mean? It means basically the expansion will be in powers of z minus 2. And by the way, I forgot to mention it, all this kind of work, you can actually find it on my website. If you go to the tab advanced, and I think I got things like that. I think there is something that's called complex variables. So I don't have that many questions because I've started adding very recently. Soon I'll probably add a few more if I get the time. So this 4 questions, I picked it up from a booklet in there. So let's look at this expansion. What do we do with something like that? Ideally, for something that has a sign, we want to use the standard power series for a sign which is well known, of course, yeah? So the problem is this argument, which is a mess. The question is, I'm going to use a little substitution. Do I substitute, let's say, w for all of that, or do I put W is just the denominator? Both of them, I guess they will work, but because I have transformed this as well, it might be a good idea to just call W. I'm going to write it here, actually. W, for the time being, is Z minus 2. So, consequently, Z is going to be W plus 2. So let's see how that changes my function. Let's call it f of W now quite clearly. F of W, Z plus 2 is of course W plus 4. So this has changed to W plus 4. And the sign now is the sign of 1 over W. It's not too bad. Okay, so we can do some kind of expansion. This is going to be W plus 4. The standard expansion for a sign of something is going to be square bracket x, so that's 1 over W, minus cubed over 3 factorial, so it's going to be 1 over, the 3 factorial is 6, and this will be W cubed, okay, and then it goes plus, it's going to be 5 factorial, so it's going to be 120 W to the power of 5 plus higher order terms. Okay, and now I need to tidy this up. I just need to multiply it, so I'm gonna do it in 2 lines, in some kind of like a grid. It's W times all of this, so that's going to be a 1, W times 1 over W, minus W times this is 1 over 6, it will kill it to W squared at the bottom. Then it's going to go plus W times that. It will reduce the W at the bottom to W to the 4. And then I go 4 times that, 4 times that, 4 times that. Unfortunately, the powers don't, that I'm not getting the same powers. And I didn't leave space in between. So what I'm going to do, I'm going to put them on the gaps here. So, of course, it's plus dot, dot, dot if you want. And 4 over W, so that probably a natural place to put it is here. 4 over W minus 4 over 6 is going to be, so I'll cancel it, 4 over 6, let's cancel it, 2 over 3 W cubed, so that's in between those two, and then I got 4 over 120, which is a 30th, so that's going to be plus 1/30th. And the power, of course, that doesn't change, it's going to be W to the 5. So looking at this expansion now, this Laurent, it only has a left branch. If you think about it, the highest term in ascending powers of W is 1. So it's from 1 and then it goes to the left. So probably I will start, this is actually the lowest term I have recorded, plus it should be minus, but it doesn't really matter. It goes something like this, basically. Okay, so I'm going to start putting dot, 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 1 over 30 W to the 5 plus 1 over 120 W to the 4, and then minus 2 over 3 W cubed, there, and there's a minus again, minus 1 over 6 W squared plus 4 over W, and then it terminates on the far right with a plus 1. And you're gonna spare me, please, for this particular one. It hasn't finished, of course, because we're not in W. W was our construct. We put W just so we can do the expansion. So it's just literally just rewriting all of these things here. Okay, with the W's all replaced with the bracket, of course. So the first term would have been 1 over 30 Z minus 2 all to the power of 5 plus dot, dot, dot. Just replace all of this, and that is the Laurent expansion of example number 3. So this was a little bit different. It required the substitution, but standard results, the expansion of sine of x or sine of W, whatever you want to call it, and it was reciprocated as well. So we had to be a little more careful with this. And the fourth one now, and final one for today, I'm pleased to say, is an f of z. That's a little bit different because it's asking for different things. It's also, we're going to connect a little bit with this definition. So f of z is equal to e to the 2z over z minus 1 all cubed. What does he actually say? Determine the Laurent series for this about its singularity. Okay, so it doesn't tell us what to use, about what point we will expand, and hence state the residue of f of z about this singularity. So we'll ignore the second bit. So first of all, we're going to think about, okay, where is the singularity? Well, the exponential function starts with 1, and then it's got other bits. It doesn't play any role of this. We suspect, of course, the singularity is, of course, at positive 1, and it's a triple pole. That's what every normal human being would have said. So we're going to expand about in powers of z minus 1. So how are we going to do this? We would like to, this is going to be a little bit of a pain. I think probably you have to do the similar thing to what we've done with the sine, which is to use a little substitution, because I would like to use a standard expansion for that, but I like powers of this. So what I'm going to do, I wrote z minus 1 of that. Let me just write it again. W is equal to z minus 1. So I'm going to change that to w cubed. So my z is going to be w plus 1. So this is going to be now, if you want, an f of w. And my f of w is going to be e to the 2 bracket w plus 1. But my denominator now is nice, 1 over w cubed. Which, of course, on the next line is going to be e to the 2w plus 2 over w cubed. And of course that is another, if you want, times e squared. And I'm going to rewrite this as e squared over w cubed times the exponential of 2w, which is a standard series which we can quote. So that's actually not bad at all. It doesn't look that bad. E squared over w cubed. The exponential function is, of course, 1 plus, I'm writing in x, sorry about that, because I've run out of letters, x, w, z's, and so on, plus x cubed over 3 factorial plus dot dot dot. So my argument there is 2w, so it's going to be 1 plus 2w plus 4w squared over 2 factorial, another 2w squared, because it'll cancel with the 2 from the 2 factorial. And then I'm going to have 2w cubed, so I'm going to get the w cubed, 8 over the 3 factorial, which is 6, so that's going to be 4/3 there, plus terms of at least w to the 4. And after that, it's just a case of just multiplying it all out. The question says, does it say find the Laurent? Yeah, it does say find the Laurent. I'm going to leave it explicit, this one. I'm not doing sigma. It's going to be a little bit of a mess. I hope you allow me to do two things. One is to multiply, put the squares obviously in every single term, but at the same time, after I cancel the w's, to be going back into z's according to the substitution that I used. So I hope I don't make any mistakes. E squared over z minus 1 all cubed plus 2 e squared, coefficient is squared, and now will leave me z minus 1 all squared at the bottom. It should follow a pattern. The w cubed will reduce, will be increasing the powers now from z minus 1 cubed all the way up. So this one is going to be another 2e squared, and at the moment I'm not even thinking, I'm just copying, following a pattern. I don't need the bracket there, to the 1, and then I have a 4e squared. Of course, now there should be, of course, the w cubed cancels the w cubed. There'll be no z minus 1 plus dot 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 if you want. So this is the Laurent expansion for this particular function in z. This is what it looks like. And the thing is now, it says, hence state the residue. A residue. What is a residue? I don't know if I briefly mentioned it. We'll be using it a lot now in lectures to come. Residue of f of z. Okay. the residue of a function about a singularity. So it has to be. You have to say more. The residue of f of z about actually should be an isolated singularity to keep all the purists happy, about an isolated singularity. For us, it will normally be some kind of pole. Most of them will be simple poles, but it might have a few doubles, a few triples at best. Okay, oh no, I actually rubbed off what I had in there. Okay, sorry, because I want to give this an example. Was it plus, is this term here, 4, actually I don't need that one. What am I doing? I'm going mad today. Sorry again, 4/3, I didn't actually need it. Okay, so let's go back. A residue of a function f of z about an isolated singularity usually will be a pole for us. And usually not just a pole, a simple pole, simple, double, triple at best. Okay, is the coefficient, and simple pole, let's say at the point z is equal to c, is the coefficient, a lot to write, I hate writing, is the coefficient of z minus c to the power of -1 in its Laurent expansion, and goes without saying about that pole at z or in powers of z minus c. Okay, so if you look at this particular function, the f of z is e to the 2z over z minus 1. Quite clearly that has a pole of order 3 because the Laurent expansion starts with 1 over something cubed in powers of z minus 1. Okay, so we've done this expansion, and this is the very, very special term. I mentioned on lecture number 1 why this term is very, very important. When it comes to integrating, it's the only term that has a contribution. The rest over a closed contour that contains this kind of singularity, or a singularity if you want, it has no contribution. This one has a contribution, and the residue is actually the coefficient of this term. This is the residue for this particular function. So when the question is asking, and hence state the residue, the answer for that one is 2e squared. Okay, it can be 1, of course, because of course if you expanded something and it was blah 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 1 over z, don't forget that's just a 1. If it was a -1 and so on. This is very important for what we're about to do. We rarely, in the questions that we're likely to see, will be computing residues, but computing Laurent expansions. But you need to know what it is, where is it coming from, and if we need to use Laurent to get a residue, you need to understand what we're doing and why we're doing it. Most of the residues that we are likely to compute, they'll be coming from little techniques, a little formula which I'm going to introduce the next time, which is based on the Laurent. You're timesing something by this Laurent by something in order to kill some of these terms before, in order to read off this coefficient essentially. But we're not going to look at the formula or prove it or anything like that. We're just going to go straight. There's a formula, just use it, find residues. Okay, so I hope you got an idea if you on Laurent what this is all about. Okay, and I hope I see you very soon. Who's laughing now? I'm certainly laughing. I'm going to go and have something to eat, guys. Okay, see you soon. Bye now.